Well, we talked a little bit already in the last video about F is equal to ma, Newton's second law. And we said that's pretty much equivalent to this idea, which is weight is equal to the mass times the gravitational constant. Well, what's really going on? How are these two connected? Let's see here. If I had a block, this is a block right there, and I put it on a table. Okay, here's my table. We'll make the table in black here. Okay, so I have a block and it's sitting on the table, and we already know that the weight of this block can be calculated as the mass times the gravity. Now, what would happen if I took away this table? As it turns out, if I took that table away, which I can magically do here, there, okay, it disappeared. Okay, if I took the table away, guess what? This would actually fall with an acceleration which is that of gravity. In fact, these two would be exactly the same, 9.8 meters per second on Earth. So this g actually simply indicates the acceleration this block would have if we had nothing underneath to hold it. And remember this 9.8, it feels this acceleration, it feels the pull of acceleration whether it is moving or whether it's not moving, right? So in other words, if I take the table away and it can move, it will accelerate at that. And if I have the table here, it can't accelerate, but it's still feeling that pull of gravity the same as if that table wasn't there. So it's just, that's what causes it to actually exert a weight or a force down on that table. Now, let's say that I want to figure out how fast a ball would be moving if I dropped it. And you may think that this is, well, who would really care about how fast a ball would be falling if you drop it? But you'll see there's actually a use for these kinds of things. As it turns out, and trust me, it took thousands of years for people to figure out something that looks really straightforward, so it's actually not as straightforward as you think, except once we see the answer, it seems to follow pretty easily and naturally. What this is saying is, if I take a ball and I have some initial velocity on that ball, okay, so let's say that I take it and I'm holding it in my hand. So what is its initial velocity? Oh, well, 0, because I'm holding it, right? And then I let the ball fall. Okay, so it starts to fall, and I'm letting the clock tick as it's falling. And here it goes, it's falling. So at every second, the new velocity can be computed by just taking the time, however many seconds it's fallen, multiplying it by whatever its acceleration is, and since it's on Earth, we're going to assume it's almost 10, and then we can find the final velocity. So let's go ahead and calculate this just like they do in your book. they have a little table, and it says position, and then it says fall time. So you can imagine that this might be a person jumping out of an airplane, which I've never done, but I've always wanted to do it, sort of, kind of. And the velocity, that would be how fast I would be falling once we got out of the airplane, and the acceleration. And you're going to see, I'm going to try and play a trick on you. Okay, so let's say that I'm the ball, in some sense. This is actually me. I'm jumping out of an airplane here, and I'm going to start falling. And so I'll call my airplane position, just for ease of use, we'll say, even though this may be like 10,000 feet up, we're going to call this 0. And then however far it falls down, we'll call that a minus number, right? So we can say that at time 0, I'm not letting it fall very long. I'm at position 0, so I'm at a height of 0. And my velocity is, well, I'm going to plug this in. If my initial velocity is 0, because I'm just sitting still, and I fall, so that's 0 right here, and I fall for 0 seconds, then my final velocity has got to be 0 too. Do you see that? You've got a 0 here and a 0 here, right? So that multiplies out to be 0. And what was your acceleration? I'm going to try and trick you here. Your acceleration is you're falling, and so you are feeling the acceleration of gravity. And since it's down, we'll put a minus 9.8 meters per second. So even though you don't have any velocity, you do have some acceleration, right? It's just like that moment in an elevator where you get in and the elevator starts down, and you're just starting to accelerate downwards, right? So there is an acceleration going on there. Hopefully it's not minus 9.8, because otherwise that means your elevator is falling. But you are feeling that acceleration. And now let's say that you are at time t is equal to 1 second. Okay, I'm going to erase above this. We're going to just plug in more. Okay, so this is time t is equal to 1. Okay, what's the acceleration? Acceleration is always the same, minus 9.8 meters per second. So you plug in minus 9.8 right here, and that's multiplying, so I'll put a little dot right there. It's times 1. And what was our initial velocity? It's 0. So now you have, let's see, minus 9.8. Okay, so it's minus 9.8 meters per second. Notice this is meters per second. This was acceleration, so it was meters per second squared. Now what if I want to calculate this last little part right here, the position? Well, to do that, I would use this formula, which they also give you. And I don't want you to get confused about all this stuff. So just realize that you can calculate the position using this formula, plus 1/2 AT squared. So if I asked you to calculate the position at time t is equal to 1, what would you do? You plug here, t is equal to 1, except it says to square it. So I'm going to do that. See, 1 times 1, and that turns out to be 1, of course. What is A? A never changes. It's going to be minus 9.8. I'm not going to write the units in right there, but we know that it's meters per second. And then times 1/2. Why is this? Because this is our magical formula. We figured out that this formula will actually, ooh, did I forget something? Yes, I did. There. Copy that down quickly. Okay, I put a T right here. Okay, so now we're trying to calculate how far this has fallen. So we plugged in all of this stuff in green. See, we got all of that. Now this part is actually very easy because VI, that's our initial velocity, was 0, right? So it doesn't matter how many seconds it goes, it's still going to be 0. And our initial position, we said that was 0. So all we have to do is take 1/2 times 9.8 and times the rest of this stuff. So that turns out, if we calculate that out, to be minus 4.9 meters. That's how far it would fall. Now that just gives you a sense of how to calculate, how they calculated those things in the table. And trust me, a lot of what we do in this course won't be, dealing with specifics like this, but this gives you a sense of how we can use equations to model physical reactions. What if we wanted this to go at a faster velocity, right? We wanted it to really be going. How could we make it go at a faster velocity? Well, a couple of different ways. One way is we could throw it down, right? Start it out with a downward throw so that we would have an initial velocity right here, and that would make it go faster, so that at any later t, it would be going at a faster velocity. We can let it fall for a longer time. That's why when skydivers first start falling, they're not going very fast, but the longer they fall, the bigger their velocity becomes, until they reach terminal velocity, when the air rushing past them is actually kind of holding them up a little bit. Another way we could increase their velocity would be to increase gravity. So if we dropped our skydiver on Jupiter, they would fall really fast, and they wouldn't last very long, but that's the way it goes for skydivers. What if I took a ball, and instead of letting it fall and it's starting with an initial velocity of 0, let's say that I took that ball and I wanted to throw it up. Boom, right? So it had an initial velocity, and that initial velocity is going to be really, really big. It's going to be 29.4 meters per second. That's actually 96 feet per second, so that's pretty fast. And we throw it up, and we're going to do the same thing again. We're going to calculate its, well, we'll put it down here. We'll put its position, the fall time, the velocity, and the acceleration. Okay, so go like that. Okay, first we're going to let the fall time be 0, right? So it's going to be right at the very beginning of when we let things go. And remember, we're throwing it upwards, so that's going to be a positive direction right here. So, we say fall time, but that just means how long has it been in the air. So when time t is equal to 0, it has an initial velocity of 29.4 meters per second. So we'll say plus 29.4 meters per second. What's its acceleration? Come on, what is it? It's got to be, what? Always minus 9.8 meters per second, because it's always just being pulled down. Even at the beginning, when it's going upwards, it's slowing in its velocity because it's being accelerated in a reverse direction down towards ground. So its initial position was 1 meters. Now, okay, let's go let it fall for 1 second. It's actually rising while it's doing that. So now I'm going to erase this. Erase. There we go. Okay, so we're going to plug in times, well, t is equal to 1. Acceleration is minus 9.8 meters per second, and the velocity is 29.4. So we're going to have a final velocity. Look at that's 29.4 minus 9.8 times 1, which is just minus 9.8. And so that turns out to be 24.5 meters per second. So we'll put that in right here. 24.5. Oh, wait a minute. Did I get that right? Oh, I'm sorry. No, I got that wrong. We'll just erase that. That's very easy to fix. And we'll put 19.6 meters per second. That makes more sense. Okay, so then right down here, we'll put 19.6 meters per second. And acceleration, haha, that's toughy, but we've got it, 9.8 meters per second. And what's the position? Now we're going to plug everything in. We started out at an initial position of 0. And let's see, VI was 29.4, and times 1 second. Whoops, 1 second. Plus 1/2 times minus 9.8 meters per second times 1 squared. Okay, when we work all of that out, it should turn out to be 24.5 meters. So we put 24.5 meters right here. Okay, now we plug in 2, fall time at 2 seconds. And when we do that, we're going to erase everything here. Okay, got it. Okay, so we got 2, let's see, 2 seconds squared, and then minus 9.8, and then 1/2. This is going to be 2 seconds right here. And VI, we remember, was 29.4. Okay. And then plus XO, and that's 0. And that is gives us our final XF here of, it should be 39.2 meters. So 39.2 meters. And that's, and then if we want to calculate the velocity at that time, we'll go right back up here to this equation right up here, and we'll plug in everything, and now it'll turn out to be, well, we had our initial velocity is 29.4, and then plus, what is A is minus 9.8, and then times 2 seconds, and we work that out, and it should be 9.8 meters per second. Okay, so this is 9.8 meters per second, and this is still minus 9.8 meters per second. That's the acceleration. It's always being accelerated the same. And it turns out when we plug in the numbers at for 3 seconds, that will be, it's going to be going up and up and up and up and up and up, and it's just at the point where it's just reached 0 velocity. And when you plug everything in to these equations, just the same way we've done as before, you will find that at 3 seconds, the height that it's achieved is 44.1 meters, and it's 0 meters per second because it'll have just reached the top of its little trajectory. And of course the acceleration is always minus 9.8 meters per second. Alrighty, so here we can see exactly what we've just calculated. At 0 seconds, we're throwing it up. It has an upward velocity, an initial one. 1 second, see how this purple vector right here? A vector is just an arrow that indicates both the size, the magnitude, and the direction. And velocity is actually a vector quantity. It's got 2 things going on. You know, it's got a certain speed, magnitude, and it's got a direction. So notice how the velocity is beginning to slow down as it gets over here by the at 1 second. Then it's going still slower at 3 seconds. Well, it's supposed to be a 0 velocity, and it is 0 vertical velocity. It's got a little bit of sideways velocity on this one, you can see. And then it starts speeding back down. So whatever happens on the going up is happening in the reverse as it goes back down. So if it took 3 seconds to go up, it's going to take, again, another 3 seconds for it to come back down. Now, one thing to be aware of is, let's move this little guy out of the way here, come back here. Notice how if we drop a ball or we throw it sideways and let it drop, it actually, at each second, it's falling at the same rate. It may not look like it, but at, whatever this time is, maybe t is equal to 1 second, these will both hit the floor at precisely the same time. So the sideways motion is independent of this vertical motion. So you throw it sideways or you throw it down, it doesn't really matter. It'll hit the floor at the same time. Just if you add a sideways component, it'll hit further away, as this shows. Now let's say you threw a ball down a field, something like that. Okay, so you throw it down the field. There it goes. How can you throw it farthest? If it turns out that if you throw that ball up at a 45-degree angle, that will keep it in the air as long as you can have it in the air, while also having as long a distance as you can. See, this, if you throw it at this angle, it'll keep it in the air longer, or it'll allow it to go higher, but it won't go as far. If you take it at a low angle, it'll hit the ground before it can really travel much distance. It's at 45 degrees that you have the optimal trade-off of, you've got loft, and which gives you time, and also at a good angle to get some distance. Notice this trade-off idea. Trade-offs, as it turns out, are some of the most important ideas related to engineering. Engineers always have to think in terms of trade-offs. So one very well-known academic, Mike Hammer, did a study of all businesses worldwide, all of the top businesses, to try and see if he could figure out what it was that they had in common that could help them to be such great businesses. And he found something very interesting. All of the top CEOs, you'd think, what would they be trained as? Accountants, businessmen, something like that? No. All of those top CEOs were originally trained as engineers. Now, why would engineers be at the top of the best-run businesses worldwide? Hammer supposed that it was simply because engineers are taught to think in terms of trade-offs. They know that everything, you can throw it higher, but you won't get as far, or you can throw it lower and you still won't get it as far. There's an optimal point where you can balance issues and come up with the best trade-offs involved. For example, you might think, oh, well, an engineer must design a car to make you safe, right? And yes, they work towards that. But to design the optimal car in which you would scarcely ever have an accident, you'd be talking gallons per mile. I mean, such a car would be incredibly heavy, incredibly difficult to turn, just a real behemoth, and nobody would want to drive or buy something like that. It would be so expensive. So engineers have to think in terms of trade-offs. Yes, we want safety, but we've also got to keep in mind that we've only got so much gas money. We have to use common sense as far as that goes. So again, the big issue for engineers is that they think in terms of trade-offs. Let's have a little fun with this moving man video. Okay, first I'm going to turn it on and watch this. Okay, notice that as I move him, his position changes, his velocity changes, and the acceleration with which he's moving also changes. Right? There we go. You should have a little fun with this yourself, but you can see, let's stop it for a minute. Okay, what I want to show is watch how the velocity will change, and as he speeds up, the acceleration will be positive. As he slows down, the velocity is still positive, but the acceleration will be negative. So let's try that again. We're going to reset everything. Yes, we want to reset it. Okay, here we go. Now, I have a positive velocity. But see, every time I slow down just a little bit, whoops, crashed. Every time I slow down just a little bit, that acceleration changes as I do that. So you can kind of get a sense there of what's going on, how the velocity, when each time the velocity increases, this acceleration goes up into a positive number. Each time the velocity gets lower, even though it's still a positive number, so we may be going in this direction, but if we're slowing down, our acceleration is negative. Now we can see that with the use of vectors. So let's put vectors. Those are arrows that indicate the direction. Now let's see if I can take this order. Oh, let's just reset everything again, and we'll go like this. Okay, now off we go. Okay, now watch. I'm going along in this direction. Every time my little finger gets a little bit slow, the acceleration becomes negative. So you can see a little bit of the forward velocity, but well, we just crashed and burned there. But anyway, now the velocity is negative, and the acceleration kind of bobbles back and forth as I speed up and as I slow down. I love this little guy. Okay, now let's look at some of the charts. Now again, all I have to do is get him to start moving. You can see how the position goes up. He's increasing. Velocity is changing, and of course the acceleration is changing at the same time. Okay, now his position has stopped. He's right here at 8 feet, something like that. Velocity, he's not going anywhere anymore. And likewise, of course, he's not accelerating. Okay, we're going this way. So you can see, as long as I'm speeding up negatively, we get a positive acceleration. Or actually, let's see if we can stop this thing, and we're going to try it one more time. Clear. Okay, let's speed him up negatively. Now watch as I speed him up. Oops. You can see at the very beginning when I started to speed him negatively, it was accelerating negatively. And as soon as my finger jerked to a halt, it bobbed back up there as far as the acceleration. Then it continued down when I was trying to do that. Now let's make him accelerate positively. Okay, well, I could do it for a little bit until my finger started waggling. You can see how the velocity changed. Here's the velocity in a positive direction, velocity in a negative direction, well, you can't see it now because it's all cleared off, but this is a really fun little animation to play with, and it's right there on your PowerPoint as far as what the HTML or the URL is.
Since the release of our instructional video, An Engineer's Guide to Cats, and a rise in popularity of cat yodeling, many people have expressed difficulty in achieving yodeling with their own cat. The first ingredient needed for cat yodeling is a cat. Selection of a cat with the correct temperament is critical. You will want to find a cat that is mellow enough, yet still capable of being annoyed. You should not apply any physical discomfort, but it is advisable to use protection for the first yodeling attempts in case of excessively jubilant yodeling. The first phase of cat yodeling is the annoying phase. This involves simply cradling the cat in a loving manner for a short amount of time. Other methods for increasing the annoyance of the cat include something called the semi-automatic kissing machine, and also a technique for cross-species sensitivity training called the overly friendly sniffing dog simulator. Finally, a momentary vertical displacement of 4 to 6 inches will trigger the vocalizations of the cat, whereupon a gently applied shiver will complete the yodel. Advanced yodeling technique involves sequential application of all of these yodel elements. Cat yodeling has many advantages. It develops an affectionate bond between the cat and the human. It exercises the vocal systems of the cat. And it brings beauty into the world as a new form of artistic expression.